Swayam Prabha. Digital India. Educated India.
Hello students, welcome to lecture number 9 of this module, that is propulsion mechanisms and functional applications of micro nanobots. So in this lecture we will be discussing the chemical, magnetic and light driven propulsion strategies in detail. So let's start. As we have already learnt in our previous lecture that micro nanobots require efficient propulsion at a very small length scale. So these are very minute, these are very small in size, so they will require efficient propulsion at that scale because they have to deal with a lot of resistance via the viscous drag forces that is dominating in the low Reynolds number fluid. So these these are dominated by viscous forces and low Reynolds number physics. So in fluid where the Reynolds number is low and viscosity is high, the micro nanorobots will require a very efficient propulsion mechanism to move ahead. So propulsion strategies determine the functionality and application domain. So why are these propulsion strategies important? Because these are going to determine what functions your bots are going to serve and also the application, the purpose for which they are designed. So these are inspired by biological microorganisms and synthetic nanomaterials. So these are inspired by biological microorganisms, as I've already told you that bacteria move via flagella, sperms are moving and bacteria move, and the protein kinesin that also works on the microtubule. So there are many natural bot-like structures in our body already and all around us that are moving. So nature has designed these machines. So now we are inspired by these machines and we are trying to create this this synthetic micro nanobots that are of small size, and their size matters because the cellular size is larger than, like, even the red blood cells are in the micrometer range, and your the size of the cell, these microbots and nanobots, they are smaller than the size of the cell also. So they can go inside the cell and they can serve any function that you can manipulate them accordingly. For whatever function they are required, you can manipulate your bots accordingly. So as we have already discussed in our previous lectures that the physical constraints that act at the micro nano scale, so motion occurs in low Reynolds number regime. So your micro nanobot is of a very small size, so its motion is basically governed by low Reynolds number regime. That means that the motion is affected by a high viscous force as compared to the inertial force. Okay, so your viscosity is dominating over the inertia to move forward. So at that small size, motion is governed in low Reynolds number regime and inertia is negligible compared to the viscous drag. So reciprocal motion cannot generate propulsion. So as we already know that the back and forth motion is not generating any net displacement, so it is not generating propulsion of your bots. Then asymmetry and non-equilibrium process are essential. So your symmetrical bots are going to make a to and fro movement which is not generating any net movement, any net displacement. So asymmetrical design is required for your bot to move ahead. So let's make a quick revision. At low Reynolds number, viscosity dominates motion. The concept is that the low Reynolds number compares inertial forces versus viscous forces. So at very small scales and low speed, Reynolds number is rho VL by mu. Okay, so this is very, very less in case of a viscous fluid, where rho is the fluid density, V is the velocity, L is the length, characteristic length of your bot, and mu is the viscosity of the fluid in which your bot is supposed to move. So for micro nano systems, Reynolds number is equivalent to this much, 10 to the power minus 3 to 10 to the power minus 6. It comes in this range. So it means fluid behaves like a thick honey. Okay, so when Reynolds number is very very less, it means that viscosity is very high and your fluid is going to behave like a honey. So momentum does not carry motion forward. Whatever momentum that is acting on your bot, it is not going to carry that bot forward. That a bot will not be able to move. What are the consequences? That motion will stop immediately when the force stops. Okay, so as long as you're providing a force on your bot is moving, but motion will stop automatically as the force is stopping over it, because the drag is going to pull it back again. Then moving requires continuous input energy, because the size is very small, so it has no inertia of motion. So the movement, it will require continuous input of energy. You need to put some energy in it to move, for that entity to move. Then hydrodynamics dominates propulsion. Okay, so viscous forces are overwhelming inertial forces, because viscosity is dominant. Drag force is extremely high relative to body mass. Because viscosity is dominant, the drag force is extremely high as compared to the body mass of your moving entity. So Newton's laws behave differently, and motion is governed by Stokes' law instead of Navier-Stokes turbulence. So your drag force is equals to 6 pi mu RVF. So basically, which means that the laminar flow is smooth. There's a smooth laminar flow, there's no turbulence, and there's a flow reversibility, that is time symmetric motion. The drag force depends on the viscosity of the fluid. So after this, Purcell's scallop theorem. This theorem states that a swimmer that performs a reciprocal motion cannot achieve net displacement in a low Reynolds number Newtonian fluid environment. Okay, so what is a Newtonian fluid? A fluid with viscosity where the Reynolds number is low. Okay, so in that environment, a reciprocal motion cannot achieve net displacement. That is what this theorem is about. So the name, this term scallop theorem, this is derived from the scallop. What do you know what a scallop is? These are mollusks that are found in seas. So have you seen the seashells that you find on the shores? These are fan-shaped shells of sea mollusks. These are bivalves. These have two shells, and this scallop theorem is derived from that. So that's the movement. See, you can see this is making a to and fro movement, which makes no net displacement. So that's a scallop, a fan-shaped bivalve. So its valves, basically this sea organism, it has no legs and no arms, and still it is able to move. It has no fins, it has no wings, and it is still moving in the sea. So how does it do that? It opens its mouth very slowly, and then it closes it very fast. So it opens it slowly and water rushes in slowly, and then it closes it very fast, and a jet of water goes out through this pore over here. So what happens is that this is slow, and then a propulsion is happening over here and pushing it ahead. So that is how it moves. So this is the scallop theorem. That is the scientist Ed Purcell, who was awarded Nobel Prize in Physics in 1952. So he discovered NMR also, which is a basis for MRI. So that's the movement of a scallop. It moves like this. It moves in a zigzag pattern. So it's like this, and then back to the same position. So what happens when the Reynolds number is greater than 1, then there is a displacement, and when the Reynolds number is very very less than 1, the net displacement is 0. So the resulting constraint is that the bots must break symmetry. So what we conclude is that the bots must break symmetry to move. So solutions are, you need helical corkscrew rotating structures like bacterial flagella, or flexible beating tails, or asymmetric deformation, or nano-reciprocal shape changes, and this is why chiral and asymmetric geometries are crucial, so that we are able to create some net displacement. So dominance of surface forces over body forces. So as I've already told you in the surface chemistry part, that at nanoscale the surface area to volume ratio increases drastically. So what happens is that surface forces dominate over volume forces. So now the forces that are acting on bulk materials, that is the inertia and gravity, they are not so dominant. So the dominant forces become the surface forces like surface tension, electrostatic forces, or van der Waals. So these are the dominating surface forces the van der Waals forces, electrostatic forces, capillary forces, adhesion forces, or hydrophobic hydrophilic interactions. So these are the forces that are dominating. So what are the consequences of the dominant surface forces? Basically, bots tend to stick to surfaces. So as we know that the dominant surface forces, they can also cause like curdling of milk. So the hydrophobic forces, they force the milk to form the curd. So that is how bots are going to stick to surfaces. So this will be the consequence of the dominant surface force that we need to counter. So movement near boundaries become difficult. Movement near boundaries becomes difficult. Then special surface coatings are needed to reduce adhesion. So bots will tend to stick together, and special surface coating will be required for the bots to reduce adhesion and maintain some distance. Otherwise, the bots are going to stick together and agglomerate, and they will not function properly. Brownian motion and thermal noise. So what happens at nanoscales? The molecules constantly collide with bots. So at such a small scale, what happens is that the molecules in the bot environment are going to constantly collide with the bots. So what will be the effect? Random jittery movement. Okay. So your bots are going to show random jittery movement because they are constantly colliding with the molecules around. Okay, so if you put something of a macroscopic object in water or any fluid, so the molecules that are colliding with it won't make such a huge difference. But if your material is almost comparable to the size of like molecules, it is slightly bigger, it's like a few molecules bigger, so it is going to collide with the molecules and it will make a difference. So what will happen is that it will create random jittery movement. And then instability. Navigation errors, you want to go in some direction, but by colliding with the molecules, your direction is getting changed. So that will be navigation errors. And influence increases as size decreases. So what happens is that smaller the scale you are using to fabricate your material, so more will be the influence of these effects. So influence will increase as the size decreases. So that is what this interference is all about. And then engineering requirements are that some stabilizing forces will be required, or feedback control systems will be required, or larger microbots sometimes preferred for stability. For stability, larger microbots are preferred. Feedback control systems, what does that mean? It means that your bot needs to sense the environment that it is in. So it will sense and change direction. Diffusion dominates over convection. So transport at microscopic scales is governed now not by flow transport but by diffusion. So diffusion time relationship, that is the diffusion time relationship, meaning smaller distances diffuse quickly, larger distances take disproportionately longer time. So implications are, these are efficient over short distances only, and these are extremely slow for long transport. These are good for drug release at local site but bad for long range navigation. So this is the consequence for this phenomena, that diffusion is going to dominate over convection. Energy constraints. So your bots cannot carry conventional battery or motors. So as you know that you put a battery inside any moving object today in any electronic item, and that makes a movement. But bots cannot carry, bots because they are of the size nano and micro, so they cannot be carrying conventional batteries with them. So these are the challenges. Energy storage is impossible at nanoscale, internal engines are impractical, and a continuous external energy source will be required. The solutions: magnetic fields, light, ultrasound, chemical fuels, and biological energy, that is enzymes and cells. So mechanical constraints and structural weaknesses. At tiny sizes, materials can fracture easily, and there is a high shear stresses experience, and flexibility versus rigidity balance is needed. But you need to design your material accordingly, whether it has to be flexible or rigid. Thus, soft materials and hydrogels are often preferred. So your soft materials and hydrogels are preferred because these materials will be more durable in varying environments. Environmental constraints. So bots must operate in either blood, non-Newtonian fluid, or mucus, cellular environments, or harsh chemical environments. Okay, so these will either work in biological environments or harsh chemical environments. So there are environmental constraints. So each has a different viscosity, pH and flow behavior. And also there are other elements inside, like in bloods there are RBCs and platelets that the bot will be meeting on its way. So your bot must operate in all these different environment and it will face some environmental constraints or environmental resistance. So that's the physical constraint, that's the meaning, and that's the effect on robots. So your low Reynolds number means the viscosity is, viscous forces are higher than inertial forces, and the effect is that your motion requires constant energy and force. Then physical constraint, high viscous drag, then Stokes flow dominates, which means no momentum based motion. Scallop theorem is a physical constraint where symmetric motion will be ineffective. The to and fro reciprocal motion will not work over here. So asymmetric propulsion will be required. Then physical constraint where surface forces dominate. What will happen is that bots will stick together. It will cause adhesion, and meaning there will be adhesion and due to van der Waals forces and all. So due to surface forces there will be adhesion between the bots. So the effect will be that there will be sticking issues and your bots are going to cluster. Then Brownian motion, which means that will create random thermal noise. So the effect will be that your navigation won't be stable. Then diffusion dominance, there will be slow mass transport, which means this is going to limit your long distance travel. Your bot can only travel short distances because of diffusion dominance. Then energy limitations, no onboard power means external actuation is required. Then mechanical limits, your bot will be fragile and deformed, so careful material choice is required. You need to choose materials that are soft and flexible. Then environmental complexity, different fluids, there are different environmental constraints like biological and other fluids, whatever fluid you are using, that will be, these are complex fluids. So a specialized design is required for your bot to move in these complex environments. So that's a brief overview of propulsion mechanism that we are going to study in detail in this lecture. So chemical fuel driven propulsion, then magnetic field driven propulsion, then light driven propulsion, and then hybrid and bio inspired propulsion approaches. So we are going to study these one by one in detail. So what is a chemical fuel based propulsion? So propulsion is generated through catalytic chemical reactions. Here, as I've already told you in my previous lecture, the propulsion is generated through catalytic chemical reactions, and local concentration gradients drive motion, and this typically involves asymmetric surface functionalization, and this is well suited for autonomous operation. So what is chemical fuel based propulsion of micro nanobots? Micro nanobots often use chemical reactions with surrounding fluids. What are they going to do? They are going to use chemical reactions with the surrounding fluids as a source of energy for autonomous propulsion. So they are going to move on their own by using chemical reactions with the surrounding fluids. This method is widely used because it provides self-sustained motion without external motors or magnetic fields. So you don't need to provide any external energy source. You are using the internal energy source of the microbot by making it interact with the surrounding fluid as a source of energy. So what is the basic principle behind this? The robot surface is coated with a catalyst. Okay, so your robot surface is coated with a catalyst like platinum, gold or manganese oxide that reacts with a chemical fuel, that is hydrogen peroxide or glucose. So your robot surface is coated with a catalyst and it is put inside a chemical fuel. So the chemical reaction generates gas bubbles, which is oxygen in the case of H2O2. So these gas bubbles are going to propel the bot via bubble formation. Okay, so that will create bubble formation and propel your bot. So ion gradients will cause self-electrophoresis and local concentration gradients will cause diffusophoresis. So this generates thrust pushing the micro nanobot forward. So that's the reaction. In presence of platinum, this is the fuel and it is getting degraded and oxygen is being formed. So these oxygens will be formed as bubbles inside the fluid, and these bubbles are going to provide a thrust for your bot to move. So these bubbles are going to collect on the surface of your bot and these will generate motion. So tiny bubbles produced by the reaction eject asymmetrically from the bot, generating net forward motion. You have your bot and you are coating it with, surface coating it with your required catalyst. Okay, so that's your bot now, which is coated by a catalyst, and it is put inside. Let's say if you are considering water purification, so you are putting it in a flask of water that is contaminated by dyes or pesticide or whatever you're trying to clean. So that's your bot, and it is coated by your catalyst, and you're putting inside this the fuel, which is H2O2 in this case. So this H2O2 basically breaks down into hydroxyl radicals, and it which goes on to further degrade, your dyes and all. So what happens is that in the reaction of this breakdown process, basically O2 bubbles are generated. So these O2 bubbles will be generated on this surface. These are the O2 bubbles. These are being generated on the as a reaction between the catalyst, and as the Fenton reaction takes place and fuel is being utilized, and this is happening on the surface of the bot. So these oxygen bubbles are being formed, and these oxygen bubbles are being released asymmetrically, and these are going to going to propel this bot forward. So tiny bubbles are produced by the reaction which eject asymmetrically from the bot. So tiny bubbles are being produced, these are being ejected asymmetrically from the surface of the robot, and this is generating the net forward motion in the fluid. So advantages: your autonomous motion is without the external fields. So there's no applied external field, and yet your bot is moving. So there's an autonomous motion without external fields. Then there's a fast and continuous propulsion. There's a fast and continuous propulsion. This can be combined with targeting for drug delivery or environmental remediation. So for drug delivery, it is not possible to use hydrogen peroxide, so we are using some other fuels, but the process remains the same. Then this works in aqueous and physiological solutions. Then limitations: this requires continuous fuel supply. Requires continuous fuel supply. There has to be fuel inside your system for this entire reaction to take place, to generate oxygen bubbles. So you need to put a fuel before it runs out. You need to put a continuous fuel supply. So fuel may be toxic at high concentration. So if you are using H2O2, like I've already told you, you cannot use it in a very high concentration because it starts to get toxic. Then bubble formation can be unstable at very small scales. So bubble formations are usually unstable at small scales, so you need to control that thing. Then motion control is less precise than magnetic actuation. So motion, obviously you cannot control the direction and navigation when you are considering this bubble propulsion mechanism, because bubbles are all coming out from all directions, and that is a spontaneous production of bubbles. So you cannot control the motion very precisely. You cannot be steering. You cannot be steering in any particular direction. So that is not possible with this chemical propulsion. So what are the design considerations? Your bot has to be asymmetric or Janus design. What is Janus design? When one side is coated with catalyst for directional motion. So let's say that's your Janus particle. One side is coated and one side is coated either with something else or it's uncoated. So that creates an asymmetric design. So the design needs to be asymmetric or Janus type, that is one side is coated with catalyst for directional motion. Catalyst selection: high activity at low fuel concentration. You choose a catalyst that has a high activity at low fuel concentration to reduce toxicity. So what catalyst are you selecting? You are selecting some catalyst with a high activity which works at low fuel concentration. so that you have to use less of the fuel if the fuel is toxic. So it will work because of the high activity of your catalyst. So surface functionalization, which is drug loading, targeting ligands or stabilizers. So for drug loading and target, there can be surface functionalizations, like if you want a particular drug to reach somewhere, so you're going to surface functionalize your bots. That is, you're going to add some functional groups over it. If you are targeting some ligand, so you are going to create, if you are targeting a ligand, so you are basically surface functionalization, you are doing this surface functionalization of your bot with that particular receptor of that is specific to that ligand or stabilizers. So that is what surface functionalization is all about. So when you are targeting a ligand, basically you are putting on the surface of your bot the corresponding receptor. Then environmental compatibility. This must function in biological fluids or environmental water. So your design consideration should be such that your bot is able to function in biological fluids or environmental water. So you're going to keep this in mind. Types of chemical propulsion. So these are the 4 types of chemical propulsion mechanisms. These can be self-diffusiophoresis, self-electrophoresis, bubble propulsion mechanisms, or enzyme powered propulsion. These are the 4 types of chemical propulsion mechanisms. So that's the comparative table between each types of chemical propulsion mechanism. So self-diffusiophoresis mechanism is a local solute gradients drive the motion. So there's a change in local solute gradient, and there's a change in local solute concentration, which creates a gradient across and which will help in driving the motion of your bot. So examples are enzyme coated nanoparticles in glucose. Advantages: there's smooth propulsion and your material is biocompatible. Limitations: speed is low and it is sensitive to environment. Then self-electrophoresis. It works by creating ionic gradients which generate electric fields. So it works by creating ionic gradients that generate electric field. Examples are platinum gold nanorods and hydrogen peroxide. Advantages being directional motion possible, motion is possible, and autonomous. So if you want to create directional motion, you want to be direction specific, so you use self-electrophoresis. Limitations: this needs conductive medium, conductive medium, and it is also sensitive to ions. Then bubble propulsion, where mechanism is gas bubbles are ejected from the catalyst surface. Examples being platinum Janus-spheres and tubular microjets. Advantages: high speed and this overcomes Brownian motion. Limitations are fuel toxicity, bubble instability, and less precise control. Enzyme powered propulsion. The mechanism is biochemical reaction that generates microflows. Then the examples are catalase or urease coated bots. These are the enzyme coated catalase or urease coated bots. Then advantages: these are biocompatible and these use natural substrates. These are using natural substrates. So that is the advantage. Then limitations: it is slower and it is substrate dependent and you need enzyme stability. So chemical fuels used in micro nanobots. So these are the examples of the various chemical fuels that are used in fabricating your micro nanorobots. These may be hydrogen peroxide that is decomposed on platinum surfaces. So this is the catalyst and this is your fuel. So hydrogen peroxide decomposition that takes place on platinum surfaces. So that's an example of a hydrogen peroxide based fuel. Then glucose and urea, this acts as fuel for enzyme powered systems. So that acts as a substrate or fuel. Then environmental pollutants as alternative fuels. So you can also utilize environmental pollutants as alternative fuels. So you are basically trying to degrade environmental pollutant, and you're also using them as fuel for your bot to move. So as long as your pollutant stays, your bot is going to move through it and also break down the same thing. So biocompatible fuels for medical use. So that's a comparative chart. The fuel type, hydrogen peroxide. Mechanism, it decomposes to release oxygen bubbles. Then typical system is a platinum coated Janus bots. Advantages, high propulsion speed. Limitations, it is toxic at high levels. Then applications, lab experiments and microjets. Fuel type glucose. Mechanism is enzyme based. Reaction create gradients. Then typical system, glucose oxidase driven bots. Advantages, biocompatible. Limitations, it is slower. And then applications, used for drug delivery and biosensing. Then fuel type urea. Mechanism, enzyme catalysis producing ammonia and carbon dioxide. Typical system is urease powered bots. So advantages is that it can work in a body. Limitations are it is substrate dependent. And then applications, biomedical navigation. Then environmental pollutants, redox or catalytic degradation providing thrust. So you are basically degrading the environmental pollutant and also generating thrust out of it. So that typical system is catalytic remediation bots are typically based on this fuel type. Then advantages, it is fuel independent. You don't require a fuel because you are using your environmental pollutant only as a fuel, so you don't require any additional fuel. So this can be eco-useful. Then limitations, it is pollutant dependent. As long as the pollutant stays inside it, so your bot will be able to move, otherwise it will stop. So applications, water cleanup. Fuel type, biocompatible body fuels. Mechanism, physiological reaction based propulsion. Typical system, used in enzyme powered nanobots. And advantages is that it is safe for humans. Limitations, lower energy. And applications in vivo nanomedicine. Then let's come to magnetic field driven propulsion. So external magnetic fields generate torque or force. So when we are trying to move something in an external magnetic field, it is generating a torque or force, magnetic force. Then helical inflexible structures convert rotation into translation. So you are using helical inflexible structures that convert rotation to translation. Then precise and reversible control of motion. There is a precise and reversible control of motion. It does not require onboard chemical fuel. So magnetic field driven propulsion, it does not require any additional fuel for your bot to move, because it is moving by your external magnetic field and also its shape, that is helical and flexible structures. So what are the design principles for fabricating magnetic bots? So for magnetic propulsion, these are the design basics, that is incorporation of magnetic materials. At first you need to incorporate some magnetic material into your bot. That is the first step. So you incorporate some iron nanoparticles or nickel or any magnetic substance that is going to move in your magnetic field. So or second thing is you are giving some geometry that will help in the increasing the propulsion efficiency. So you are using helical or chiral geometries. Usually you are using helical or chiral geometries. Then synchronization with external field frequency. So your bot needs to be highly synchronized with that field. Then compatibility with biological environments. So that is also the last step, but very important step, that it needs to be biocompatible for the environment that it is going to move in. These are the design principles for magnetic propulsion of micro nanobots. So magnetic propulsion is widely used for remote, non-invasive and precise control of micro nanobots, especially in biomedical environments. So in biomedical environments, magnetic propulsion is widely used for remote, non-invasive and precise control of micro nanobots. So this is, let's start with incorporation of magnetic materials. So the principle is micro nanobots are embedded or coated with the magnetic materials to generate torque and propulsion under an external magnetic field. So common magnetic materials are iron, nickel and iron oxide. These are the common magnetic materials that we are using. Then that's the formula for magnetic torque, where tau is the torque on the micro nanobot. This is the M is the magnetic field, magnetic moment on the robot, and B is the external magnetic field that you are providing. So that's the magnetic moment of the robot, and that's the external field that you are providing. So that will be tau will be the torque generated on the micro nanorobot, and that is how it will move. So torque rotates the robot combined with helical geometry. This produces linear propulsion. So your bot has a helical geometry. So your bot is having a helical geometry and you are applying magnetic field. So what is happening is that this field combined with the geometry is producing linear propulsion. So this field you are providing, and this bot, this is helical, this has a helical structure, so you are providing a field, and this has magnet inside it. So this will move linearly when you are providing a field over here because of its unique geometry. Helical or chiral geometry is the principle behind this is that in low Reynolds number, as I've already told you, in a fluid with low Reynolds number, that when the viscosity is high, it will require a non-reciprocal motion to generate net propulsion, which was defined by the Purcell's scallop theorem. Then helical or chiral shapes convert rotation into forward translation. So that is the propulsion velocity, where v is the linear velocity of the robot, this omega is the angular rotation rate, that is radian per second, and then this is the geometry dependent factor, which is function of the helix pitch, radius and length. So this is the design tip, that you need to optimize the helix pitch, you need to optimize radius and filament thickness for maximum propulsion efficiency. So that's the design tip. You need to optimize the helix pitch, the radius and the filament thickness for maximum propulsion efficiency. Synchronization with external field frequency. So the principle is the rotation speed of the magnetic field determines the angular velocity of the robot. The rotation speed of the magnetic field will determine the angular velocity of your robot, and proper synchronization ensures efficient energy transfer and prevents slipping. So you need to have a proper synchronization between your magnetic field and your bot to ensure that there is a efficient energy transfer. Okay, there is no energy loss, and this prevents slipping. So that's the expression. V is the linear velocity, which depends on the geometry factor and rotational drag coefficient, which is equals to 8 pi eta r square for sphere, and then B is the magnetic field strength, Nm is the magnetic moment of the robot, Nf is the field rotation frequency. So above a certain frequency, the robot cannot keep up with the field, which will reduce propulsion efficiency. So that is the shortcoming, that above a certain frequency, the robot will not keep up with the field and it will reduce its propulsion frequency. So there's also rotational drag in fluid, which is determined by Stokes' law. So this is the rotational drag coefficient. So drag is not only in one single direction, it can also be rotational drag. So this is the rotational drag constant. It depends on the dynamic viscosity of the fluid and radius of the robot. So this is important because the applied magnetic torque must overcome viscous drag. So now your applied magnetic torque also needs to torque also needs to overcome the viscous drag. So that's the expression for your applied magnetic torque, and that's the rotational drag coefficient. So your magnetic torque depends on the viscous drag force. So it needs to overcome this for forward movement. Compatibility with biological environments. So these are the design requirements. The biocompatible coatings, PEG, PLGA, these prevent immune reaction. Polyethylene glycol or PLGA, these prevent immune reaction. So these biocompatible coating will you to make your bot more compatible with the biological environment they are going to be put in. Then size optimization for capillaries, that is 5 to 20 micrometer for microbots and 100 to 500 nanometer for nanobots. So you need to optimize the size of your bots. And then if you are considering biological environment, so depending on the function, you need to create a size optimization for your helical structure must allow smooth propulsion without damaging tissues. So your structure is helical, it can just go inside any tissue and damage this. So it must allow a smooth propulsion. Light driven propulsion mechanisms. So there's light driven propulsion mechanism which uses optical energy to generate motion. So now after magnetic propulsion we come down to optical energy used to generate propulsion. This is light driven propulsion mechanism. So these depend on the photothermal and photocatalytic effects. So these are remote and spatiotemporal control is possible. So minimum chemical contamination is present in this method. These are the mechanisms of light driven propulsion. There is photophoretic motion due to temperature gradients. So in light driven propulsion there is photophoretic motion due to temperature gradients, then photocatalytic reactions on semiconductor surfaces, or optical gradient and scattering forces that we are going to study in detail, and then thermophoretic propulsion. So let's start with the mechanisms of light driven propulsion. Light driven propulsion uses light energy to induce motion in micro nanobots through temperature gradients, chemical reactions, or optical forces. So now you are using light to drive your bot. So light driven propulsion is going to use light energy to induce motion in your micro nanobot through temperature changes, creating a temperature gradient, or chemical reactions, or optical forces. So let's start with photophoretic motion, that is temperature gradients. So the principle is there is uneven light absorption on your bot that is going to generate a temperature gradient across the particle. So your light is falling in one direction, and it will create uneven light absorption that is going to generate a temperature gradient across the particle. So the surrounding fluid produces thermally induced flow pushing the particle. So the surrounding particles, basically it will create temperature gradient, that a cooler layer, warmer layer, this kind of temperature gradient will be formed, and then there will be a thermally induced flow that is going to push your particle. That's the equation for photophoretic force, where your photophoretic force is directly proportional to the temperature gradient across the particle. So your photophoretic force will depend directly on the temperature gradient across the particle. So more is the temperature gradient across the particle, more will be the photophoretic force, and faster will be the movement of your bot. So your particle moves from hot to cold side, or vice versa, depending on the particle properties. So depending on the particle properties, your particle will move from hot to cold side. So it's like, that's your particle, and you have uneven light falling onto this, okay, from all sides, some uneven light falling onto this, and what will happen is wherever light is falling there will be some increase in temperature. So there will be temperature gradients created all across the surface of this particle. Somewhere it will be cold, somewhere it will be hot. So it will depend on the direction of the light, and because of the uneven light falling on that on your particle, what will happen is that there will be a temperature gradient created, that is a hot side and a cold side. So your particle is going to move from hot to cold side, or whatever, it can also be vice versa, depending on the particle properties. Photocatalytic reactions, the principle is that light excites a semiconductor particle, that is TiO2, producing electron hole pairs which catalyze chemical reactions in the surrounding solution. So this works on the principle is that light is going to excite a semiconductor particle and produce electron hole pairs which catalyzes the chemical reactions in the surrounding solution. This reaction produces gas, ions, or chemical gradients, creating propulsion. So this reaction is going to produce gases and ions or chemical gradients that create propulsion. So TiO2, this is light is falling upon it, H mu, and then it is creating electron and hole pair. So this is going to create a chemical reaction and propulsion. Propulsion velocity depends on reaction rate, light intensity, and gradient symmetry. So your propulsion velocity is going to depend on reaction rate, light intensity, and gradient asymmetry. The reaction example, that's H2O2 going to form H2O and O2 in the presence of TiO2 and H mu. So you have a light and you have a catalyst, that is photocatalytic reaction, where light is falling upon it in presence of catalyst, and there's a fuel like this. So here what is happening is that your electron hole pairs that are generated, these are going to these are going to initiate your reactions. These will create the hydroxyl radicals, and that is going to function for the catalytic degradation of whatever contaminant you are planning to target. Optical gradient and scattering forces. So that's the principle. Optical tweezers are used to create light intensity gradient. So optical tweezers are used to create a light intensity gradient, and particle experiences gradient force and scattering force. So this is the equation where F optical is equals to F gradient force and F scattering force. So that's your optical gradient, that is this is the gradient force and the scattering force. So your gradient force is equals to this. So where this is the total optical force, alpha is the polarizability of the particle, this is the local light intensity squared, and this is the radiation pressure from the scattering photons. So what is the result? Thermophoretic propulsion is the resulting phenomenon. Thermophoretic propulsion, the principle is localized light absorption creates a thermal gradient in the fluid. Localized light absorption will create a thermal gradient in the fluid, and the particle moves along the gradient via thermophoresis. So the equation is this, where this is the thermophoretic velocity, this is the thermophoretic mobility, which depends on the particle and fluid properties, and then this is the temperature gradient. So that's the equation for this thermophoretic propulsion. Then comparison of propulsion strategies. What is the chemical propulsion? Which is your chemical propulsion was autonomous but fuel limited. So this was autonomous, but it did not require any external fuel, it was moving on its own. It was autonomous, but it was limited by fuel. You needed a constant supply of fuel for chemical propulsion. Then magnetic propulsion, it needs high controllability. You need magnetic field to control your magnetic propulsion. Then light driven propulsion basically creates precise spatial control. And then hybrid systems, they combine multiple advantages. So we also use hybrid systems of propulsion. You mix and match these propulsion strategies and create a better system. That's the comparison of propulsion strategies of micro nanobots. Chemical propulsion, the driving mechanism is catalytic or enzymatic reactions producing bubbles or chemical gradients. Advantages, autonomous, fuel driven and simple design. Limitations, fuel limited, potential toxicity and less precise control. Then propulsion type is magnetic propulsion. Driving mechanism, external rotating or oscillating. Magnetic fields acting on embedded magnetic materials. Advantages, high controllability, remote steering and suitable for biomedical applications. Then limitations, it requires external fields and fabrication complexities. Light driven propulsion, the driving mechanism is photophoretic forces, photocatalysis, optical gradient scattering and thermophoresis. The advantages, precise spatial control, remote, non-contact and tunable by light intensity. Limitations, limited penetration in tissue. As you know, your light is going to have a limited penetration inside your tissue. It is not going to penetrate your tissue very deeply. So it will be need for surface functions only. So it has limited penetration in the tissue and the force is small. So the thrust generated will also be small, and then it requires light accessible environment. So it will require only light accessible environment. So it will only function where light can, as far as light can reach, it will only function till there. So that is the limitation of light driven propulsion. Then hybrid systems, this is made by the combination of chemical, magnetic and or light propulsion. So you combine these all accordingly and create a hybrid system. Advantages is combines autonomy, control, precision, and this can be entirely multifunctional. Then the limitations, the method may be complex. The fabrication method can be complex, and then integration challenges, and it is difficult to integrate all three propulsion mechanisms into one, and it may require multiple external inputs. So that's the functional applications of micro nanobots, that is targeted drug delivery and therapy, minimally invasive surgery and diagnostics, environmental remediation and sensing, and in micro scale assembly and manipulation. So your functional applications for targeted drug delivery, this can be used, or minimally invasive surgery and environmental remediation and sensing, and microscale assembly and manipulation. These are the biomedical applications. So, your bot can navigate in complex biological fluids. There's an on-demand drug release. Your bot goes inside and it releases drug on demand. There can be a sustained release of drugs in case of bots, and cell manipulation and biosensing. Then reduced systemic side effects. There are reduced systemic side effects. Environmental and industrial applications. So, pollutant degradation and removal. Your bot is required for pollutant degradation and removal. Then your bot is required in water purification systems. Your bot is also useful for chemical sensing and monitoring, and then in catalytic microreactors. So these are the environmental and industrial applications of your micro nanobots. So summarizing the lecture, the propulsion mechanisms are central to nanobot functionality. So your propulsion mechanisms are these are very important for your microbots to function properly. So chemical, magnetic and light driven strategies dominate. So these are the strategies that we are using: chemical, magnetic, light driven strategies or hybrid strategies to propagate for the propulsion of your micro nanobots. Then each mechanism offers unique advantages and limitations. As we have already seen, there are unique advantages to every propulsion mechanism, and also there are many disadvantages associated with every propulsion mechanism. So there are interdisciplinary design drives the future applications. So you need interdisciplinary design for future applications. Okay, thank you.
Hello and welcome to this piece of literary snippet. As a student of English literature, the kind of poetry that we are most likely to encounter is perhaps the sonnet. Now, a sonnet, as some of us might already know, is a poem which is composed by putting together 14 lines of verse, and this style of poetry was first popularized by a poet named Petrarch, who lived in Italy during the 14th century. Now, legend has it that Petrarch once saw a very beautiful lady by the name of Laura, and Petrarch was so enamored by the lady that he wanted to compose poems to celebrate his love for her. But there was a problem because marriage was impossible. Petrarch himself was an ordained priest, and that prohibited him from marrying. And the lady herself was a married woman. But nevertheless, Petrarch went ahead to immortalize the beloved and his love for that lady in poetry, and the form that he chose was the sonnet. Since then, sonnets have traditionally been written about ladies who are of unparalleled beauty, and about poets who are hapless lovers and who know that their love for their beloved would have to remain unrequited forever. Now, in England, the sonnet form came around 16th century, and its first practitioners were people like Sir Henry Howard, the Earl of Surrey, and Sir Thomas Wyatt. However, it was William Shakespeare who was to prove the greatest of English sonnetteers. And in fact, the charm of those sonnets that Shakespeare wrote 400 years from now still can be felt. And if I read out to you one of Shakespeare's sonnets, you'll appreciate this better. This sonnet is usually known by the title, "Shall I Compare Thee to a Summer's Day?", which is also the first line with which the poem begins. Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date. Sometime too hot the eye of heaven shines, and often is his gold complexion dimmed, and every fair from fair sometime declines, by chance or nature's changing course untrimmed. But thy eternal summer shall not fade, nor lose possession of that fair thou owest. Nor shall death brag thou wanderest in his shade, when in eternal lines to time thou growest. So long as men can breathe or eyes can see, so long lives this, and this gives life to thee. Now, as you might have noticed, that very much like the Petrarchan sonnet, this poem too speaks of an idealized lover who is more beautiful than a lovely summer's day. But also notice how, in the last few lines, the poem subtly shifts from praising the beloved to praising the poet himself. It is the poet who is going to produce the lines of poetry which will preserve the beloved's glory forever. And people will continue reading them even after the beloved has died. As the last couplet of the poem suggests, so long as men can breathe or eyes can see, so long lives this. And here this, of course, refers to the verse that Shakespeare composes and which we are reading today, 400 years later. So long lives this, and this gives life to thee. Shakespeare is well known for these kind of subtle plays with the conventions, these kind of subtle reversals of what is expected conventionally. But nothing is more striking than the sonnets that he composed on a dark lady. In these poems, we do not meet the traditional fair, idealized beauty, but rather a woman whose appearance might even be described as ugly. Here is a sample. My mistress's eyes are nothing like the sun. Coral is far more red than her lips is red. If snow be white, why then her breasts are dun. If hairs be wires, black wires grow on her head. I have seen roses damasked red and white, but no such roses see I in her cheeks. And in some perfumes is there more delight than in the breath that from my mistress reeks. I love to hear her speak, yet well I know that music hath a far more pleasing sound. I grant I never saw a goddess go. My mistress, when she walks, treads on the ground. And yet, by heaven, I think my love as rare as any she belied with false compare. As you can see, the beloved described in this poem is nowhere as beautiful as a beloved of the first poem. Yet, the point that Shakespeare is making here is that though the image of the beloved is not as beautiful as it was in the previous poem, it doesn't stop her from being an object of love. Love, Shakespeare insists, has very little to do with the outward appearance of a person. And in many ways, this de-idealized beloved is perhaps a person with whom a more intimate engagement is possible. She is definitely a more human person, a person who treads on the ground, just like all of us do. See you in the next episode of Literary Snippet.